One more concept from basic equilibrium that we'd like to review before we start discussing the systematic treatment of equilibrium is the formation of complex ions and how the formation of complex ions affects the solubility of specific water-insoluble ionic compounds. There are a couple of general concepts besides the first pass calculations that you get from the KSP when you're trying to calculate the molar solubility of a metal under specific solution conditions that you need to consider are the common ion effect, which we reviewed a little bit on Friday, but there's also the formation of complex ions, which leads to the common observation that above a certain concentration of an anion or a ligand, inorganic compounds that we typically would assume are uniformly water insoluble tend to get more soluble as the concentration of the anion increases around them. And this is contrary to what's predicted by the common ion effect and contrary to what would be predicted by Le Chatelier's principle if it wasn't for the fact that when we talk about the dissolution of an ionic compound, we typically talk about just the breaking apart of the metal cation from the nonmetal anion, and we don't consider the effect of complex ion formation on the solubility of the precipitate through Le Chatelier's principle. So here we're just going to briefly review complex ions. We're going to introduce you to a different notation than what you may have seen before, which is the concept of a beta value, which is very similar to a typical equilibrium constant expression, but is used in a slightly different way. So as our example when discussing the solubility of inorganic compounds in water, we're going to talk about the precipitation and dissolution of lead-2 iodide. I attached a video of the precipitation of lead-2 iodide to the front piece for today's lecture. And for those of you who have seen lead-2 iodide before, you probably will not have forgotten it, although you might have forgotten that the precipitate in question is lead iodide, because lead iodide forms this obviously bright yellow kind of snot-like precipitate when you combine solutions containing lead-2 plus and iodide in water. It's a fairly water-insoluble salt with a KSP value of 7.9 times 10 to the negative 9th. And just as a refresher on terminology, when we're talking about precipitation reactions, we refer to the metal ion, lead-2 plus, as the Lewis acid, the electron pair acceptor, and the iodide, the anion, as the ligand, the Lewis base, the electron pair donor. The KSP expression is, of course, lead-2 plus concentration times the concentration of iodide squared. So based on what we know about the common ion effect, we would predict that as the concentration of iodide goes up in solution, the ionic solid lead-2 iodide must become more insoluble to satisfy Le Chatelier's principle. However, experimental observations would predict the opposite, whereas there's a certain threshold value where if you bump the iodide concentration up beyond that threshold value, the lead iodide actually becomes more soluble. And this is something that you can see generally just with your eye, but also by probing with a number of different experimental measurements. So what's going on in this case? Well, what we're overlooking when we calculate the molar solubility of lead-2 plus just based on this single solubility equilibrium is the formation of complex ions. So for instance, if I have lead-2 iodide, PBI2, can pick up a further mole iodide anion, the ligand, to form the complex ion PBI3-, where a complex ion is a general term for an ion that exists and is composed of simpler ions bonded to one another. So PBI3- is an example of a complex ion and would of course form by a further mole of iodide reacting with the PBI2 solid and forming this complex ion. And this is why the formation of these complex ions explains why under high enough concentrations of the ligand, you can actually achieve better solubility of lead iodide in highly concentrated iodide solutions. there are a series of equilibria that extend beyond the formation of lead-2 iodide into the formation of PbI3 minus, PbI4 2 minus, the formation of these complex ions. So when we think about the solubility of a metal cation or an ionic compound composed of a metal cation under specific conditions, we have to take this extending series of equilibria into account and consider how Le Chatelier's principle affects the whole related series of equilibria. Now, there are two ways to represent the formation of PbI3 minus in equilibrium terms. In general chemistry, you might have been introduced to the first of these, which is known as an equilibrium formation constant, or a KF, which describes the formation of PbI3 minus as the reaction of PbI2 solid with a further mole of I minus to form the complex ion PbI3 minus. There is another type of equilibrium constant that we can use to describe this reaction, which is mostly a note-keeping or terminology thing, where we can also treat the formation of the complex ion PbI3 minus as 1 mole of Pb2 plus reacting with 3 moles of iodide to form this directly. And we could write a typical equilibrium constant expression for this, products on the top, reactants on the bottom, and it would be the concentration of PbI3 minus divided by the concentration of Pb2 plus times the concentration of iodide cubed gives us the equilibrium constant for this reaction. And under these conditions, rather than referring to this as a KF just by convention, we refer to a formation constant for an ion written this way as a beta value rather than a K sub F. And there's a particular utility to using these beta values to describe the formation of complex ions, in that we can easily calculate the concentration of Pb2 plus and I minus in a saturated solution of PbI2, or any solution where we know that the solution is saturated with a lead-2 iodide solid and the concentration of iodide is known, which makes it easy to calculate the concentration of these complex ions in a series of related equilibria. And the way you would use beta values is to describe the series of all the available complex ions that could form using related equilibria, some of which are described by beta values, some of which are described by Ks. And the convention is that if you're describing your equilibrium constant stepwise, the formation of this species, then that species, you refer to the equilibrium constant value with a K. If you're bypassing the stepwise mechanism and you're saying the starting materials, lead-2 plus reacts with X number of moles of the ligand to make this complex ion, you refer to it as a beta value rather than a K. But a beta value is just another type of equilibrium constant, which is framed to talk about the reaction as occurring between the metal cation and X number of moles of the ligand, rather than talk about the formation of these complex ions stepwise. So if we want to talk about the overall solubility of lead-2 iodide, the first thing I want you to recognize is that we're not actually just talking about lead-2 iodide breaking apart to make 1 mole of lead-2 plus and 2 moles of I minus, which would be described by the KSP. We're also talking about a series of related complex ions forming, including PbI plus, the complex ion that would form before PbI2 solid precipitates. We're talking about the formation of the small quantity of PbI2 that's actually borderline soluble in water. So when you're thinking about a series of equilibria and you want to get as accurate an answer about the system as possible, you have to recognize that everything is to some extent soluble, even if it's only very sparingly soluble. So even though we consider PbI2 solid to be an insoluble precipitate, it's not only not truly insoluble in the sense that some of it dissolves to give you these ions, but some of those PbI2 complexes are actually soluble. They can form the neutral complex PbI2 in water. If your lead-2 plus picks up 3 moles of iodide, it can form the complex ion PbI3 minus. If the lead-2 plus bonds with 4 moles of iodide, it can form the complex ion PbI4 2 minus. The key thing I want you to recognize here is that when we're talking about solubility equilibria for water insoluble ionic complexes, there's a whole series of related equilibria that describe how soluble the ionic compound will actually be in water. And so when we think about Le Chatelier's principle impacting the solubility of lead-2 iodide in water, we need to consider the effect of all these equilibria because lead and iodide are involved in each of them. And each of these reactions is described by its own equilibrium constant. We use the K sub F notation in the case of the formation of PBI+, but because of how these reactions are written, we use beta value notation for the equilibrium constants for the last three reactions here, where the K value for the PBI+ formation is 1.0 times 10 to the second. The beta value for PBI2 aqueous formation is 1.4 times 10 to the third. For PBI3-, we just revealed the beta value as 8.3 times 10 to the third. And for PBI4-2-, the beta value is 3.0 times 10 to the fourth. Each of these values is a statement of an equilibrium constant. And so when you are writing an equilibrium constant expression for a beta value, remember that it is just another type of equilibrium constant and it is written the same way. It's just a note-keeping thing whether we refer to it as a beta value or a K sub F. And the bottom line is what this means is that for lead iodide, like most water-soluble inorganic compounds, the overall solubility as a function of the ligand concentration is going to have a local minimum where at low concentrations of the ligand, Le Chatelier's principle drives the ionic compound to break apart and dissolve. At intermediate concentrations of I-, you would have a local minimum in solubility, where up until this region, the common ion effect controls the solubility of the complex. And then beyond a certain concentration of the ligand I-, you actually have an increase in solubility, which is governed by complex formation, and a lead-2 iodide is made more soluble at high iodide concentrations by virtue of Le Chatelier's principle. The idea being that the more iodide is around, the more of the complex is driven to form PBI4-2-. And so you have a Le Chatelier's principle sort of sink where at extremely high iodide concentrations, the iodide is used up not only making PBI2, but actually making higher order complex ions like PBI3- and PBI4-2-. So the formation of these complex ions can drive the water solubility of PBI2+ to be actually higher at high iodide concentrations than it would be at kind of intermediate iodide concentrations. And the beta values allow us to make quantitative predictions rather easily about the concentration of any lead-containing species in a lead iodide solution under specific conditions. But to make accurate determinations of the lead species concentrations, we have to look at this whole series of interrelated equilibria in detail and make use of the beta values. So for instance, we can use the beta values and the KSP to calculate the species of all calculate the concentration of all lead-containing lead iodide species in a saturated solution of PBI2 if we know the concentration of dissolved I-. So for instance, if we know our whole series of complex ion formation equilibria and have the beta values, we're in a position to rather easily answer an intimidating question like, what is the molar concentration of all the lead iodide complex ions in a of all the lead iodide complexes and complex ions in a saturated solution of PBI2 solid containing dissolved iodide with a concentration of 0.001 molar?